Welcome to Research Reels.
Modern portable electronics face a critical contradiction in their power management design. Battery life is paramount, yet devices need both stability and responsiveness under rapidly changing load conditions. Today, we're diving deep into an elegant solution published in the IEEE Journal of Solid-State Circuits by Mohammed Al-Shouk, Hoi Lee, and Raul Perez that breaks through conventional design limitations in low-dropout regulators. The evolution of portable devices has created increasingly stringent performance requirements for LDOs. Power management engineers know all too well the challenge of simultaneously achieving four critical specifications that traditionally work against each other: low dropout voltage, high output current capability, minimal quiescent current at no load, and excellent transient response. This research delivers a breakthrough approach that achieves all four without compromise. Their primary objective was creating an LDO that could simultaneously achieve minimal quiescent current while maintaining stable operation across the full range of load currents without relying on problematic low-frequency zeros for compensation. Let's examine the core challenge their research addresses. In conventional LDO design, delivering high load current with low dropout voltage requires a large PMOS pass transistor. This creates a large gate capacitance, introducing a troublesome low-frequency non-dominant pole within the unity gain frequency of the regulation loop. Previous approaches to this problem either consumed excessive quiescent current or relied on imprecise low-frequency zero compensation techniques, creating a fundamental design trade-off. The technical significance of this problem cannot be overstated. When using a large PMOS pass device, the parasitic pole created at its gate can seriously degrade stability. Previous solutions to this challenge have taken two main approaches: using emitter-follower buffers with low output resistance to drive the pass device gate, pushing the problematic pole beyond unity gain frequency, but requiring high quiescent current when high load current capability is needed, creating low-frequency left-half plane zeros to provide positive phase shift, compensating for the negative phase shift from the non-dominant pole, typically through ESR0 or frequency compensation techniques. Both approaches introduce their own problems, especially under varying load conditions, where exact pole zero cancellation is difficult to achieve. ESR0 techniques are particularly problematic with small output capacitors, causing large output overshoots and undershoots during load transients. The authors present a fundamentally different approach with their Buffer Impedance Attenuation technique, or BIA. At its core, BIA employs a dynamically biased shunt feedback mechanism in the buffer stage to dramatically reduce its output resistance. This pushes the problematic pole at the gate of the pass device to much higher frequencies without requiring large quiescent current consumption. Let's examine the specific implementation. Traditional source-follower buffers face a fundamental limitation. To decrease output resistance, they must either increase transistor size, which increases input capacitance and degrades the preceding stage, or increase bias current, which increases power consumption. Both options represent undesirable trade-offs. The authors overcome this through an ingenious feedback arrangement using a vertical parasitic NPN transistor as a shunt feedback device. From a small signal perspective, when input voltage remains constant, but output voltage increases, the drain current of the source follower transistor increases, which in turn increases the base current of the NPN transistor. This increases the collector current, effectively reducing the output resistance by a factor approximately equal to the current gain, beta, of the NPN transistor. Mathematically, the output resistance of this buffer with shunt feedback is expressed by the following formula, where G sub M21 is the transconductance of the source follower transistor, and beta is the current gain of the NPN transistor. For a typical NPN transistor with beta 10, the output resistance is reduced by approximately a factor of 10, effectively pushing the parasitic pole at the pass device gate to frequencies an order of magnitude higher. The researchers then enhanced this concept by implementing a dynamic biasing scheme using two additional PMOS transistors, M24 and M25, that increase current through the buffer as load current increases. This results in a further mathematical reduction of output resistance as seen in the following formula, where G sub M24 represents the additional transconductance from the dynamic biasing. This creates a buffer whose performance automatically scales with load demand. consuming minimal current under light loads while providing enhanced drive capability precisely when needed under heavy loads. The proposed buffer design provides several key advantages. Reduction of both input and output impedance of the buffer by decreasing C sub 1B and R sub EOB values, dynamic scaling of buffer performance with load current, optimizing power consumption, improved slewing of the gate drive during load transients, enhanced charging and discharging of pass transistor gate capacitance during transients, ability to use smaller source follower devices, further reducing input capacitance. For frequency compensation, the researchers employ current buffer compensation implemented with a small compensation capacitor and a common gate transistor. This technique provides significant benefits. Eliminates the right half-plane zero that would otherwise exist, ensures only a single pole dominates within the unity gain bandwidth, achieves good phase margin across the entire load current range, requires only a small compensation capacitor, 10 picofarads, enables stability without relying on any low-frequency zero. The small signal analysis performed by the researchers demonstrates that the loop gain transfer function can be approximated as a second-order system, represented by the following formula, where P sub 3 dB and P sub N1 are the dominant and non-dominant poles, respectively. The mathematical analysis confirms that over the entire load current range, only a single pole exists within the unity gain bandwidth, ensuring unconditional stability. The minimum phase margin occurs at a specific load current condition, which can be mathematically identified by differentiating the figure of merit with respect to the pass device transconductance. The resulting equation for the compensation capacitor needed to ensure stability is as follows. By using the impedance-attenuated buffer, which results in smaller source follower device size and consequently smaller C sub 1, the required value of C sub C is minimized. In the author's implementation, a mere 10 picofarads was sufficient to ensure stability across the full load current range, small enough to be integrated on chip. The LDO was implemented in a 0.35 micrometer twin-well CMOS process with a die area of only 0.264 square millimeters. The performance metrics achieved are remarkable. Quiescent current, 20 microamperes at no load condition, maximum load current, 200 milliamperes, dropout voltage, 200 millivolts, current efficiency at full load, 99.8%, output capacitor, 1 microfarad, ceramic, maximum transient output voltage variation, 54 millivolts, 3% of V underscore out for 0, 200 milliampere load step, transient undershoot, 20 millivolts, 1.1% of V underscore out, phase margin, greater than 65 degrees across entire load current range. The measurements confirm several key performance aspects. Quiescent current increases with load as intended, validating the dynamic biasing approach. Transient response shows well-behaved settling without excessive ringing or overshoot. With only a 1 microfarad output capacitor, maximum output voltage variation remains within 3% during massive load steps. Phase margin stays above 65 degrees across the entire load current range. The maximum undershoot of 20 millivolts represents only 1.1% of the nominal output voltage. Line regulation performance is excellent, with less than 3 millivolts change for a 1 volt input variation. To quantify performance improvements, the researchers used a figure of merit, FOM, that evaluates trade-offs between response time, quiescent current, and maximum load current, where T sub R is the response time given by C sub L dV sub out, I sub L max, with dV sub out being the maximum transient output voltage variation. Compared to previous designs, the proposed LDO achieved the lowest FOM value, 0.027 nanoseconds, improvement of at least one order of magnitude over other LDOs designed for portable applications, superior current efficiency, 99.8% versus 94.3% for comparable designs, better transient response with a smaller output capacitor, no requirement for ESR0 compensation, excellent transient settling behavior. The authors concluded that their proposed BIA technique with dynamically biased shunt feedback provides a superior solution for LDO design in portable applications. By pushing the parasitic pole at the gate of the pass device to sufficiently high frequencies while maintaining low quiescent current, they achieved stability across the full load current range without any requirement for a low-frequency zero. As quoted from the paper, the proposed buffer with dynamically biased shunt feedback reduces both the input and output impedance of the buffer by decreasing the values of C1b and ROB, respectively. In particular, the reduction in the value of ROB increases with the load current. As a result, P2 is located at sufficiently high frequencies under different load currents, while the LDO only dissipates low quiescent current at no load condition. The research suggests several potential future directions: application of the BIA technique to other power management circuits, further optimization of the dynamic biasing approach, integration with advanced process technologies, exploration of alternative feedback devices for different process technologies, development of adaptive biasing schemes for further efficiency improvements. For power management engineers, this work demonstrates how innovative circuit topologies can overcome conventional performance limitations. The buffer impedance attenuation approach offers an elegant solution to one of the most persistent challenges in LDO design, enabling significantly improved battery life without sacrificing transient performance, a critical advantage in modern portable electronics. Looking at comparative performance, the LDO achieves current efficiency of 99.8% at full load, compared to 94.3% for a state-of-the-art design published in 2005 for embedded microprocessor applications. The FOM of 0.027 nanoseconds is nearly an order of magnitude better than previous designs. Most importantly, it achieves excellent transient response with a small 1 microfarad capacitor, compared to the 4.7 microfarad capacitor used in designs from 1998 that still exhibited much larger output voltage variations. Mathematically, we can understand the technical significance by examining the pole locations. In conventional designs, the pole at the gate of the pass device might be located at frequencies as low as tens of kilohertz, well within the unity gain bandwidth. With the BIA technique, this pole is pushed to megahertz frequencies, far beyond the unity gain frequency, creating a robust single-pole response. The authors have demonstrated a technique that fundamentally resolves one of the most persistent challenges in LDO design, delivering a solution that can simultaneously achieve the 4 critical performance requirements that were previously thought to involve unavoidable trade-offs. For engineers developing portable and battery-powered systems, this represents a significant advancement that enables both longer battery life and more stable power delivery.